In this video, I introduce a realistic evaluation of deep semi-supervised learning algorithms. Supervised learning uses a training dataset of input target pairs x, y sampled from an unknown joint distribution pxy to learn a prediction function f theta x with the parameters theta that produces the correct target y for unseen samples from px. Semi-supervised learning uses both labeled data x, y, and unlabeled data x sampled from P so that the trained SSL model produces more accurate predictions than trained by using the label dataset D alone. Namely, the dataset DUL is used to augment f theta x with information about the structure of px. For example, DUL can provide hints about the shape of the data manifold as shown here, which can produce a better estimate of the decision boundary between different possible target values as shown here. This is the decision boundaries. Next, we will introduce pi model and VT model. Pi model trains a network for each input xi twice, which produces prediction vectors zi and zi tilde. Because of using dropout regularization, the network output is a stochastic variable. Namely, two evaluations of the same input xi and the same network width yield different results. Here shows the pi model. The loss function consists of two components. Namely, the first one is the standard cross-entropy loss, evaluated for labeled input only. And the second one, for all inputs, penalizes different prediction for the same training input xi by taking the mean square difference between zi and zi tilde. The time dependent weighting function W T is used to scale the unsupervised loss as shown here. Here is the workflow of the pi model. A virtual adversarial training uses adversarial training for consistency regularization that produces similar outputs from input and his perturbed version. Since the partial samples in the training dataset are unlabeled, namely x asterisk is either xl or xul, the objective function defined as here, where adversarial perturbation RQADV calculated from this formulation. The unknown Q is a true distribution of output labels, and P is the parametric model. RQADV is approximated by linear approximation of D with respect to R. For the L2 norm, adversarial perturbation R can be approximated by using this formulation where G is calculated from the derivative of D. Where the one-hot vector H, as shown here, approximates Q. Since Q is not available, we use current approximation P to replace Q. Namely, the virtual labels generated from P are applied to compute the adversarial direction. Using the current estimated P to replace Q, the local distribution smoothing loss function is defined as here, where RQ ADV is calculated from this formulation is virtual adversarial perturbation. The regularization is the average of LDS over all input data points as shown here, where NL and NUL are number of labeled and unlabeled samples respectively. The full loss function is given by the two terms, where L is the negative log likelihood for the labeled dataset. VT is a training method with a regularization R. Here is the training procedure of the VT model. For more details, please check with these references. Thank you. Bye.